Kia ora tātou. Kia ora. Nau mai, haere mai. Welcome to Tamaki Paenga Hira and this evening's lecture. Thank you. Thank you, volunteers in the audience. Thanks for coming out. It's an awfully cold one tonight. My name's Roger Linz. I'm the president of the Auckland Museum Institute. It's our pleasure once again to partner with the Geoscience Society to bring you tonight's Hochstetter lecture. I've been sent out to warm up the crowd in the best way possible with a health and safety announcement. So, in the event of an emergency, please follow the instructions of museum staff, such as Joseph, whom you met on the door. All exits are marked with the green exit sign. Visitor host teams wear black and green uniforms, and the security team in blue will guide us out, and we'll use the stairs, not the elevator. So with that vital information out of the way, I'll now pass over to Jennifer to introduce the speaker. Thank you.
Kia ora. I'm Jennifer Eccles from the Auckland branch of the Geoscience Society of New Zealand. And tonight we have the great pleasure of welcoming David Barrell, who is this year's Hochstetter lecturer, which is one of the Geoscience Society of New Zealand's great honours. So David is midway through his national tour where he's taking this lecture to the different centres. So in terms of the recording of this lecture being made tonight, it won't be appearing on the Auckland Museum website for about another month until David has finished his tour. So David is a graduate of the Engineering Geology program out of the University of Canterbury and took a 6-week job in Dunedin in 1992 and has been there ever since. So some of his early work was on the landslide remediation project around the Clyde Dam, and then joined GNS, where he is working in sort of the geomorphology space, being an expert in landforms, particularly of interest in terms of natural hazards and things like that. So he's a senior scientist there and is one of New Zealand's leading experts on New Zealand landforms, particularly in the Southern Alps, but has also been involved in particularly the earthquake response efforts and mapping after the Canterbury earthquake sequence and the Kaikoura earthquakes. So you didn't come here tonight to hear from me, so it's my very great pleasure to hand over to David for tonight's lecture.
Thank you, Jen, and kia ora, everyone. It's a great pleasure to be here in Auckland tonight to take you on a bit of a story through work that's been done to understand the coast of Aotearoa, New Zealand Aotearoa, and I'll be talking about the main theme tonight in terms of the title, The Sea versus the Land, Will There Be a Winner? So, I guess I'm going to start out by pointing out that in order to understand the land versus the sea, we need to, we'll start with the land. So talking about Aotearoa New Zealand being the largest part of the largely submerged Zealandia continent. I'll give an overview of Zealandia's changes from deep in the geological past through to modern times, and I'll outline how Aotearoa's landscape reflects the interplay between the rock foundations, the climate that gives the precipitation that drives the erosion, that produces the sediment, which makes its way to the coast, and the wave energy in the coastal zone, which is all part of the system. And I will emphasise that rivers and coasts are part of a system budget, and that system involves particularly material in the form of sediment and energy from the ocean waves, but also that these have been operating in a long-term regime where the coast of Aotearoa has shifted back and forth across the continental shelf over time as sea level has risen and fallen through glacial and interglacial climate cycles. So I'll explain a bit about that. Of course, the ongoing emergence from the Sea of Aotearoa is driven by plate boundary tectonic deformation. And so it's that land and the uplift and the energy from the pounding of the waves from the surrounding ocean that sets the scene for understanding our coast. And I'll frame it as a bit of a battleground between the land and the forces of the sea. And then I'll go on to explain how this whole systems idea can account for the richly varied form of Aotearoa's coastline, such as why some parts of the coastline are sort of long and sweeping, other parts are all indented with bays and estuaries. And I think that there are good explanations that will help us understand why that is. And then finally, I will share some thoughts about likely coastal changes coming in the future based on these ideas. So we're going to start with Zealandia. So the red outline on that diagram, just the water is in blue. The deeper it is, the darker the blue, and the red outline is the continent, largely submerged continent of Zealandia, and the green is emergent land. So this is a cross-section, a schematic cross-section across Zealandia at about the location of I'll just clarify, Aotearoa New Zealand refers to the emergent main part of the land of this largely submerged continent, Zealandia. And Zealandia is made of continental crust, and continental crust is thick, and so it's thick, it's buoyant, it floats on the mantle. Oceanic crust, as we see here in the grey in this diagram, is much thinner and has a tendency at margins of continents, if there's being pushed together, to subduct down under the continental rocks. So, I'm going to start with the present picture. You'll see in a number of the slides a term capital M small a, that's million annum, so 0 MA is the present day, 100 MA is 100 million years ago. As many of us will know, planet Earth's crust is broken into a set of adjoining fragments, and we call those plates, and the plates are able to move around. In this diagram, the light blue are areas of oceanic crust, and the darker colours are for the various continents, and the colours of each continent are lighter where they're submerged. So you can see that hardly any of Africa has got submerged margins, whereas almost all of Zealandia is in that light grey for being submerged. So we're going to go way back in time. So this is 420 MA. This is the start of the Devonian period. And we're looking down from over the South Pole at a reconstruction of the Gondwana supercontinent, of which Zealandia was to become part. Just point of reference, the physiography that's in this diagram, which I shamelessly stole from Wikipedia, is the current physiography of the continents. This is not how they looked back in the Devonian when they were all part of Gondwana. And you'll see... I'll see if I can get my pointer to work. Way up here is what's to become Zealandia. I say what's to become because at the start of the Devonian, not much of Zealandia was in existence. There was the what we now have as the rocks of western Aotearoa were in place by then, but much of the eastern part and many of the rocks of the South Island and the North Island were yet to be formed, and they were formed as the ocean crust was subducted under Gondwana between about 300 and 100 million years ago. Sediment scraped off, compressed and turned into rock, and that forms the greywacke rocks and the schist rocks, which form much of the spine of Aotearoa. I shamelessly stole this from Nick Mortimer. So this is 165 million years ago, middle of Jurassic period, and so Zealandia as we know it today is sort of getting mostly built. Its continental crust is forming as the sediment's being scraped off by the pan-thalassa plate, subducting towards the left in this diagram under Zealandia. And again, we're looking down from over the South Pole in this reconstruction, and I don't know, I'm not sure why it's in different languages in the bottom there. I didn't ask Nick from that when I stole it from him. And this is just going to the present day, and just to highlight that Antarctic is the only fragment of Gondwana that's more or less stayed in the same place. All the rest have been split off and shifted northward by seafloor spreading. So I'm going to run through a series of reconstruction diagrams. So this is what we call paleogeographic maps showing the lie of the land at times past. This is from a recent paper by my colleagues Dominic Strojan and others doing a reconstruction of Zealandia over the past 100 million years. So at this time, we're on the margin of Gondwana. There's been, and so this is 98 million years ago. So we've had 200 million years worth of subduction, which has just ended under Gondwana. And so at this time, all of the continental rocks, all the continental crust of Zealandia is in place. And as far as we can tell, things are pretty quiet. Subduction stopped, and there's a few dinosaurs wandering around. I'm going to zoom in just to give us a point of reference for where we are in Aotearoa, New Zealand, where all of that was at this time in Dominic's reconstruction. And so you can make out the outlines of Westland and Nelson, Fiordland, the North Island and the East and South Island, and that was approximately how all those components were arranged at this time. And the Chatham Rise is out there towards the lower right, with Chatham Islands on the end of it. So I'm going to go through this reconstruction. This is mid-Cretaceous, 98 million years ago. Subduction stopped, and Gondwana's wondering what's going to happen next. With the subduction stopped, the continental rocks of the margin of Gondwana at the location of Zealandia were starting to subside, and the pale blue colours show the sea starting to come in over the land on the Gondwana margin. By 77 million years ago in the late Cretaceous, there's still 11 million years to run before the asteroid hits and does the dinosaurs in. Seafloor spreading, so the areas of those red lines there is the continent starting to is continental breakup starting. The crust of rocks are pulling apart. Ocean crust is forming in the basins in between. So by 67 million years ago, so that's about a million years before the asteroid, the Tasman, the Zealandia is being pushed out into the wider ocean, and particularly the Tasman Sea is becoming present. This is the opening of the Tasman Sea, which is in force, and this is the separation of Zealandia and what's to become Antarctica. Tasman Sea is nearly complete in its opening by 57 million years ago, and Zealandia is becoming more and more submerged. The sea is definitely winning over the land. By the early Eocene, the Tasman Sea spreading is completed, so the Tasman Sea is as open as it will ever be, or so far. And we're starting to see a fracture propagating up from the Antarctic area. So there's a fracture and a rifting zone starting to propagate up through towards this emergent part of Zealandia. And particularly what's going to become very important is the opening of the Southern Ocean between Australia and Antarctica. There's seafloor spreading going on there, and that's shortly going to become, or shortly after this, it was going to open the Southern Ocean and start a circumpolar current. By the early Oligocene, where Zealandia can more and more submerged, the Southern Ocean is starting to form. Zealandia, Australia and Antarctica are separated. And now we're starting to see this is about time of maximum submergence of Zealandia, the smallest land area in Dominic's reconstruction. I'm just going to flick through these. The new plate boundary is becoming apparent. You can see that there's a bit of outward rotation of Australia due to the opening of the Southern Ocean, and so there are differences in the plate motion between through Zealandia, and that's by Middle Miocene as well, and truly a new plate boundary through there. And we're starting to see by the Pliocene 4 million years ago, we've taken on a recognisable shape, and that's the present day. And because it's so cool, I'm going to run through that again, because and I'm going to do it a bit faster so you can sort of see it moving. So now we're sort of twisting back the other way, that rift's opening, now the new plate boundary is coming into be. So, story so far. 100 million years ago, what is now Zealandia was part of the coastal margin of a huge continent, Gondwana, and Zealandia, Australia and Antarctica were all part of a continuous landmass. And just to emphasise that we know this thanks to 150 years and more of careful and detailed research by geologists and paleontologists that have provided the evidence that lets us reconstruct this picture. A change in plate movement saw Zealandia shunted seawards as seafloor spreading opened the Tasman Sea. So the 3-hour flight time from New Zealand to Eastern Australia has not changed in the past 52 million years. It's been that long a flight all that whole time. And so that's 25 million years of seafloor spreading at about fingernail growth rate. That's what's given us a 3-hour flight, which is, I think, a really nice way to get to get an understanding of the importance of time, even at slow rates of change, how it can all add up. Zealandia continental block relaxed and subsided, and its emergent land progressively sank beneath the sea, but then a change in plate movement saw a crustal fracture propagate through Zealandia about 40 million years ago. And by 20 million years ago, this had evolved into a new plate boundary with movement becoming increasingly compressional over time. And that's provided uplift in the plate boundary deformation zone that's enhanced Aotearoa's land area. So that's how we've got to the land that we have to work with in Aotearoa New Zealand. I'm going to talk a bit about landscape dynamics, the processes which alter and shape the landscape, and emphasise the importance of the sediment toolbox for landscape renovation. So gravel in the form of good-sized stones through to boulders. When they're moving, they become the hammers. Sand provides the abrasives, and silt and mud are the fillers that fill in the holes in between. And just to illustrate them in the landscape here, a mix of sand and gravel in this riverbed here. And in the diagram on the right, you see all these grooves in here. That's where the stream flow has been pushing gravel and sand over a silt bed, and it's cut grooves, eroded grooves and scrapes into the silt, just the work of the hammers and of the abrasives. And in places where not much movement is happening, that's when the filler, the sand, the silt and the mud will readily accumulate. This is a reservoir in central Otago. It was dam was constructed. It was filled in 1935, and out in the middle of I'm on the shore. You can see this little dark thing sticking up. They're the tops of fence posts. So that was a fence that was there before they filled before they made the dam and filled the reservoir. Our dog is about to walk into the soft mud and have to be rescued. The diagram on the right shows the sediment package exposed, where the river is cut down into that sediment package in this dry year empty reservoir. So I'm standing on the old riverbed. It's about 1.2 metres of sediment in 89 years or so. So that's 10 or 12 big floods in that 90 odd years. So that's just an illustration of the sediments in the landscape. I'm going to talk a little bit about the central South Island. The reason is that it's got varied geology, but it's also got high rates of process. It's got the highest mountains, it's got some of the greatest precipitation, and this diagram it's been drawn several times in several ways by my colleague Simon Cox. This is the version we published in our QMAP text in 2007. And it illustrates the geomorphologically most vigorous part of Aotearoa, a precipitation gradient from very large precipitation on the main divide, western flank of the Southern Alps, going into a rain shadow towards the east, steep gravel bed rivers coming from very erodible schist and greywacke rock out towards the west, and much gentler river systems out towards the east, a longer travel distance to the coast. We also have glacial lakes, so during times of glaciation, ice is formed on the Southern Alps. Those glacier tongues have created depressions, hollows, and as the glaciers melted at the end of the last glaciation, they filled with water and progressively being filled with sediment. And so there are sediment traps in the system. So not all the sediment made from the precipitation gets to the sea. And there's a degree of complexity and individuality to all these river systems, which is important to consider when we think about where the rivers meet the coast and what it means for the coastal process. This diagram here shows, first of all in white, just under the southern of Alps, that's the modern ice in the white. The bluey colour is the ice extent about 20,000 years ago, and that's mapped from the landforms left around the termini of the glaciers that form the Southern Alps. Purple is areas that would have had alpine vegetation, and the glacial outwash plains, which were built by the meltwater flowing from these glaciers, are in the yellow out towards the coast. A point to highlight is that, and we're going to talk more about this, this diagram shows the coastline 20,000 years ago, well out from the modern coast, which is here. And so this is the effect of sea level change due to glaciation globally, and we're going to talk some more about that. The Southern Alps have just got some amazing records of landscape landforms. So in many places, particularly towards the eastern side of the main divide, we have some absolutely pristine fossil landscapes which were formed during glacial times, and there's been nothing to change that ever since. So we have fossil landscapes in abundance in the Middle Eastern part of the South Island. Lake Ohau here sits in, the lake is sitting where the glacier was, it's sitting in the hole the glacier left. Around the margin you see this lumpy topography, that's the terminal moraine of the glacier. And out the front of the terminal moraine we have the meltwater outwash plains, and so that was a braided riverbed, and you can still see the braid channels there. Even though this entire thing is 18,000 years old, so there's been no change here. It's a perfect place to see history recorded in abundance. So just to update the landscape dynamic story, landscape processes are complex, and while the rivers and streams are the delivery team, moving products of erosion of the land towards the coast, it's not all that simple, and in some places the sediment gets to the coast readily, other places it's caught up and stored, and whether it's in a glacial lake or inland basins. And the important agents of geomorphological change are the sediments themselves. So the gravel are the hammers, the sands, the abrasives, and the silt clay are the fillers that generally just make dirty water, but it's sometimes very dense water, and that's quite important in the offshore area. In every catchment, whether it was a stream, river or glacier, it's got important elements of individuality in its catchment, which influences how it's been behaving through time. And I've just shown you examples of formerly glaciated catchments, which are great for understanding extremes of difference in the landscape between glacial and interglacial climate. Whereas other catchments in Aotearoa New Zealand, where they're more influenced by tectonics or by volcanic processes, will have their own styles of complexity in their behaviour. I'm doing well tonight. We've reached the coast and it's only 17 minutes in. So we're now at the coast. This is the mouth of one of my favourite places, the Rangitata River in mid-Canterbury. And we'll now talk a little bit about what goes on at sea. So I'm going to start with some background about what happens at the coast, because that's an important component of our story. So this diagram has got more than you ever wanted to know about oxygen isotopes. The main upshot is that oxygen comes in two main isotopes, oxygen-16, which is a little bit lighter than oxygen-18, different number of neutrons. And it turns out that a water molecule, which is two hydrogens and one oxygen, if that oxygen is oxygen-16, it evaporates more readily than a water molecule with oxygen-18. Now, I find that astonishing given how small atoms actually are, so we're told, but it turns out that that's how it goes, so that when water evaporates from the sea, it tends to be a bit richer in oxygen-16, and it leaves behind water in the sea that's a bit richer in oxygen-18. And that's all fine. If it's falling as rain, flowing back in, it's all well mixed, that's all grand and dandy. But when you go into colder climates and you have that precipitation falling as snow and accumulating on land as ice, that ice is made of that lighter isotope, and the sea becomes enriched in the heavier one, and we can measure that difference through time. Right, okay, so within the marine realm, the seawater oxygen isotope ratio is incorporated into the shells of marine organisms, and particularly the shells of tiny microorganisms, foraminifera, are of particular interest because they're small and they accumulate readily in seafloor sediments as sediment builds up. And by making careful and detailed measurements of variations in the isotope ratios in the shells of those seafloor sediments, provides us a measure of the amount of ice which is locked up on land through time. Now, in this rather tricky-looking diagram here, so I'm going to start. So this is 65 million years ago. That's present day. So this is the last 65 million years of time, and this is based on isotope measurements from Pacific seafloor sediments. And when you are over on this side of the diagram, when the isotope ratios are out this way, we're in hothouse terrain. There's not much ice on land. And when we're over on this side, we're in icehouse territory. There's a lot of ice on, maximal amounts of ice on land. Now, these high spiking wiggles through here are reflecting orbital variations in climate. So the Earth's orbit varies in calculatable cycles, and it means that the amount of solar radiation reaching critical parts of the Earth's surface varies over time through these cycles, and that tends to make episodes of warmer climate and cooler climate alternating between the two. The larger trends here reflect other elements of change in the system, and the most prominent one is this transition here where we went quite abruptly to more ice on land, and that's the Eocene-Oligocene boundary, and that coincides, as far as we can tell, with the opening of the Southern Ocean. So it's time that the Gondwana had split up enough to provide a through-going, and never gesticulate at the microphone. The microphone doesn't need gesticulating at. So that provided a through-going circumpolar current, which began the isolation of Antarctica, allowed cooling on Antarctica and the accumulation of the first Antarctic ice. Now, through time, that stayed sort of zigzagging similarly through to about 15 million years ago, and then there's been progressively more and more ice building up on Antarctica, and it's become real icehouse conditions globally the last 5 million, and particularly the last 2.5 million years. And now, where are we? So this is another diagram of these isotope ratios for the past 5.3 million years, and you can see the spiking here. When it's down here, that's glacial, cooler climate. Up here, it's interglacial climate, and so there's been this rhythm of cycles on about a 40,000 year rhythm, and that's the variation of the tilt of the Earth's axis, which goes from about 21.5 to 24.5 degrees, and that change in tilt affects the way that the radiation arrives on Earth and affects the climate. But in the past million or so years, we've gone into, well, first one, we see a downward trend, and so that's probably more and more ice accumulating on Antarctica. It's having a downward trend, which we're in the other diagram. But from a million years ago, we're really spiking into megacycles. They've been having about 100,000 year duration, a bit of a different pattern. So something's changed. We've gone into a real, a bit of a new game the last million years. And this is just the isotopes again, but here they've been converted onto an axis which approximates sea level. And so we talk about the climatic episodes. So climatic episodes, we've got glacial climate when things are cooler, interglacial climate when things are warmer, and state of the sea correspondingly is low stand during glacials and high stand during interglacials. So, just going to consider briefly the effects of on-land and offshore gradients on river systems. So this example here is where you've got a gravel bed river of a moderate gradient, and you've got quite a gentle shelf area offshore. The two blue lines highlight the position of high stand, sea level, like we have now, and low stand, which was most recently prevailing at about 20,000 years ago is last time we're at low stand. And then all around New Zealand we have a shelf of some sort and then a drop off down the continental slope. And this is approximately the situation of the Rangitata River in mid-Canterbury. And I've always been interested in thinking about what would happen. So if we now have a situation here with high sea level, broad shelf, if we drop the sea level down to low stand, if we drop it right down, what happens? And so we've got a gravel bed river that's going to transport gravel, because that's what gravel bed rivers do. We have quite a flattish shelf off here, so it can only push the gravel so far before the gravel can't move anymore. It's too flat to move gravel. And so we'll end up with a deposit of gravel and sand built up nearer land, and that's going to give way to sort of sand and silt that can move out across the shelf. And that'll be the profile of the low stand river at that time. So basically, this flat shelf has meant that the river will build up its bed, and not just across the shelf, but that build-ups on land as well, or on current land. That's that diagram. I'm just going to zoom in. That's a bit more visible. We'll take another example of the contrast where we have a very steep continental shelf, and so this is actually modelled on Hochstetter Harbour in Northland, and I'll just sort of show, just to illustrate the effects of what can be anticipated from sea level change on these systems. So that's the modern situation. In fact, what I'm going to do, I'm just going to start with this one here. So this was, if you like, imagine this 20,000 years ago. The sea was at low stand out here. The shelf is steep, slopes even steeper, and this river would have extended its gradient out to meet the sea. There's an unwritten rule, I've never seen it written down, probably first time just now, that rivers have to meet the sea at sea level. They can't do much else. That's just sort of how it goes. And so if the sea level changes, the river has to change to meet the sea. And so in this case, a river in this geometric setting is going to form a deep channel to cut down to that low sea level, not far offshore. The converse of the other diagram is that when the sea has risen back up to high stand, it's flooded that valley, and so sediment builds up in it. And for Hochstetter Harbour, this is the modern coastline out here, but the harbour goes an awfully long way inland, like tens of kilometres. And so this is all filled up with sediment. So there'd be a buried valley in here, and it's filled with sediment, and it's really just got enough freeboard left now that the sediment is being shifted in and out with tides. So the upshot on this is that the opening of the Southern Ocean about 35 million years ago and its subsequent and ongoing widening saw glaciation commence and then increase across Antarctica, while the global climate's progressively cooled. And the effect superimposed on that bigger change to our global environment is the variations in the Earth's orbit that cause cyclic changes in the global distribution of incoming solar radiation, solar energy, producing episodes of cooler glacial and warmer interglacial climate. And these climate cycles have become more extreme and longer in the past 1 million years. Ice now forms extensively on the mid-latitude land masses during glacials and melts away during interglacials, and that's particularly on the northern hemisphere continents where the Laurentide ice sheet forms during glacials on northern North America. The Western European ice sheet forms on British Isles, Scandinavia, and the northern fringes of Europe. So the climate's now in a situation that it's those northern ice masses particularly which are contributing to that sea level rise and fall through these cycles. So global sea level's been varying from about 0 metres at high stand during interglacials like we have today to about 125 metres below present level at low stand during glacials like 18,000 years ago. And this has had major but potentially predictable effects on rivers and coasts at all stages of sea level. So we'll have a bit of a lowdown on the low stand. In this diagram, the grey is all the area out to the 125 metre depth contour. So that's an approximation of where the coastline was at low stand 20,000 years ago. And that sea level rise began about 18,000 years ago. The red lines in this diagram are generalised and composite catchment perimeters, and blue is the east-west drainage divide. at that time. And this, just to emphasise, this is very much work in progress that is underway at the moment. And so these are preliminary diagrams that we're putting together as a resource to try and attack this problem. So, key points. No Cook Strait, no Fovo Strait, continuous landmass. Major rivers of the northwest South Island and southwest North Island converged to drain into an inlet where Cook Strait is. So there was quite a big rearrangement of the drainage at that time to make easily Aotearoa's biggest ever river. When you combine the flows of all those rivers coming in from there, you rapidly end up at 1,000 cubic annual average discharge. Now, the major river plains of today, so the Canterbury Plains, Southland Plains, Heritonga Plains of Hawke's Bay, the plains of sort of Manawatu area, they're all in places where the gradient offshore is low, so there's a very gentle shelf. You don't get them at all where the shelf is steep and narrow, whereas those steeper coasts with a steeper shelf have abundant bays, estuaries and harbours. So those alluvial plains of today are very much where the offshore gradients are low, and those indented coastlines that we have are where it's a steep offshore gradient, and that's seems to be a pretty ubiquitous observation. Now I'm just going to give a couple of examples here. Looking at Hokianga and Kaipara in Northland. So features of the diagram, we have light blue is the modern coast. This is the low stand coast out here at the 125 metre depth contour. We have a remarkable feature of the coastline along this part of Aotearoa are these huge sand dune barrier systems. And so this is a photo I took a number of years ago of the barrier system that forms Awhitu Peninsula out to the west of where we are here, and that's that spot there, Manukau Harbour. Huge dune systems enclosing the Kaipara, and then more dunes up coming inland across the top of Hokianga. The thing I want to point out is that as you go offshore, there are some pretty deep channel systems being cut. These are submarine channels, so it's never been in the air. This is the effect when you have a river system coming to the edge of the shelf at low stand, discharging down a steep slope, and it's discharging these heavily silt-laden floodwaters that are quite dense. And so out here off Kaipara we have a fan of sediment and quite a deep channel cut in it. Similarly up here in the busy part of the diagram there's a channel in here off Hokianga, which is almost certainly the Hokianga channel offshore from there. A thing which I had no idea was there until I put this diagram together recently. There's a whole lot of channels just in here in a place where there's no drainage coming to the coast. It's a place which is blocked off by this sand dune barrier. And I should add that these sand barriers, they're almost like the high tide beach, but they're the high stand beach. And they're preserved at about the high stand because the sea doesn't go any higher than that. That's as far as the sea can go. The sea can't erode them, and so that's where the sand builds up. And did it again. And it stays, and so that these barriers are the high stand beach, if you like. And the Awhitu Peninsula one here, for instance, I mean, there's late Pliocene age fossils associated with that in places. So it's been a feature of the landscape for a very long time, 3 million years or so. I would guess that this tells us that at some point part of the North Kaipara drainage has been through this barrier and discharge to a low stand shoreline and cut these channels here. And I just want to note that I've always been puzzled about why Kaipara Harbour is so big. And it wasn't until I drew this map and drew in the drainage divide that I realised it's a huge catchment. It's 7,000 square kilometres. It's half the size of the Waikato catchment. It's big. So no wonder it's got a fair bit of drainage going out through it. The other example here is the Bay of Plenty. And these are just two examples just to illustrate some of the ideas. If we go towards the south for the Rangitaiki River, this is black line is the profile. This is the profile drawn in the GIS. You can see that going to the offshore here, and ignore the irregular topography. To make this easy, I've used the Niwa's bathymetry includes land. They didn't bother cutting the land out, and so they've got this chunky, heavily, very low resolution gridded thing which you can draw a profile across. But the river gradient is about the same as the shelf gradient. In a situation like that with the sea rising and falling, it's not going to impose a big change on that river system. It's just going to sort of adjust through there. For the Wairoa system, which flows out through about the location of the Tauranga entrance, it's got quite a steep river profile, flattening out towards the coast, but then a very flat coastal zone. Now, I would have said that would be a profile that you might expect to cut down to that red line, I should just say, is the low stand shoreline in both cases. Yeah, so that's one that's a bit of a puzzle. And so I think with this work in progress, we'll be looking particularly at those ones and trying to understand what that tells us about why you've got this huge bay here at Tauranga. And just to sort of head down south, a couple of examples from down there. The shoreline, the offshore profile from Fiordland is the steepest in Aotearoa New Zealand by far. It drops straight away. The low stand shoreline's a few hundred metres out from the high stand shoreline. There's not much in it. And so it's a situation where during glaciations, when ice builds on Fiordland, the valleys fill with ice, they carve out and have calving glaciers discharging into sea. During interglacials, glaciers melt and they fill with water. And Fiordland being in quite a hard resistant rock, most of the fjords are still very much fjords and they're not filled up with sediment, whereas in more sediment-rich places they would be filled in. So it's quite a sediment-poor environment. The other contrast that shows up really well is in the southeast and South Island. So we've got Rakiura, Stewart Island here, and a very broad area of gentle shelf. I mean, it's an awfully long way out to 125 metres water depth through here. River gradients on land are quite low as well, but this is a place where the sea level rising and falling is not going to make much difference to those river systems. They'll just do what they're doing. But very different off the Otago coast, where the coast is much narrower and steeper, and at low stand, all these rivers discharged right to the edge of the continental slope, the steep one, and huge canyons formed in the edge of the shelf. And we know in many of these systems that those canyons are extended back as incised valleys onto land, quite a long way inland in some places. So yeah, that's very much a case where low stand makes the systems in size, they drown as the sea rises back to the interglacial, and in places where the sediment load is quite low, which is many of those, we have estuaries, harbours and bays, which are just even after the 6,500 years that sea level has been at interglacial level and virtually not varying, they're still full of the sea. So, just to wind things up into the heart of what we're looking at with the ideas that we're working with in this work in progress. We've got a working title of Broad-Scale Geomorphological Characterisation of the Aotearoa New Zealand coastline. And the idea is to see if we can characterise the coastline by breaking it into blocks of similar character and just seeing if we can understand more about why it's the way it is and therefore how it might respond in the future. So I've drawn a perimeter around New Zealand, out 50 kilometre wide perimeter, and I've broken it into blocks that I think are a working step for characterisation. And for each of those compartments we've assigned a range of parameters describing their character. And so tectonic environment's pretty important. What's the long-term vertical land movement, which will influence how the coast's performed. And so we've got a draft classification, and we've gone a step back into the past. We're looking for longer term things, and I'm looking offshore as well as onshore, and that's different to the NZ sea rise data set, which some of you will be familiar with, which is very contemporary. It's very much a sort of a 20-year perspective from satellite measurements. Blue means it's stable and maybe a bit subsiding, and so we can see that the eastern edge of the South Island and a fair chunk of the northern North Island are in that category. Yellow means best guess is it's stable, and that's influenced by these huge, in the interpretation, these huge high stand dune barrier systems, which seem to have been there for all the Pleistocene, if not going back further. And most rapidly uplifting parts are in the distinct uplift from Wellington around to Hawke's Bay, around East Cape, and a fair chunk of the eastern and western coast, close to the plate boundary. I mean, you can almost draw the uplift zone does relate pretty closely to the plate boundary deformation zone through here. Overall gradient of the shelf, so we've put that parameter, what's the gradient out to 125 metres depth, so we've talked a little bit about that. I've also got one for what's the gradient out to 50 metres depth, because the deeper the water close in, the less the wave energy is attenuated coming in, so it'll give a relative measure of wave energy at the coastline. That's the thought with that parameter. Degree of exposure to waves, I've devised a sort of a schema whereby how much long fetch is there. And so if you've got 90 degrees of azimuth with more than 1,000 kilometres of fetch to the nearest land, so you've got a big wave generation potential, that's very exposed, and less than that it becomes less exposed. I think the thing which really surprised me is just how sheltered things are in around the southwest coast of the North Island. It's not very exposed because the South Island's cutting out a lot of that wave energy. The other one which is in the frame here is what are the sediment sources that are available in the coastal zone? And so got a working scheme as to whether really it's mostly coming from rivers, or is it coming from coastal erosion, or some combination of the two, which will give a sense of where it's coming in from. And I guess perhaps the prime example is up in the far north here, which is green, which is all coastal, and that's because there are no rivers. You know, once you get north of Kaitaia, there's almost no land and there's no rivers, and so all the sand up there, which is the standout feature, can only be from a coastal source, and other places where it's dominantly a river source. So I think that'll be a useful attempt to characterise what the materials are in the coastal zone and where they're coming from. And the most obvious one, what's the battlefield like for the coast? Do we have eroding shores? Do we have building out shores? So that's another important component. So we come to the coastal battlefield, and we'll just finish here by looking at a few examples of how coasts vary. This example here is one of these formerly incised Otago rivers, which drains to a canyon offshore at the edge of at the top of the slope, Waikaiti River. You can see that was a valley side, that was a valley side, they're cliffed, they're eroding. This was the valley, it's entirely estuarine. The tide comes into somewhere over here, every tidal cycle, and it's got an accreting, curved sandy beach which is building outwards. So this is a very complex example of a coastal situation where you've had an incised valley that is now being filled in with sediment, and it's being done in different ways in different parts of the system. This is a nice sandy coastline. The cliffs are formed in Cenozoic age sedimentary and volcanic rocks just south of Oamaru. But the cliff on the left is eroding into last interglacial shoreline sediment. So in this cliff exposure, that's the old beach sand. It's about 125,000 years old, previous interglacial, and it's overlain by 3 or 4 metres of wind-blown loess, which accumulates during glacial periods from all the dust blowing around. This coastline is not changing in elevation at all, on the minimal change in elevation on 100,000 year cycles. This is a very stable bit of coast. Other ones, this is the Waitaki River. It's got three big sediment traps in its headwaters, 3 big glacial lakes. They trap the sediment, and so it's a very sediment poor river. I took this photo, it was discharging about 350 cumecs into the sea, but almost all that gravel is from coastal erosion further down, eroding into the old river plains. So this is an eroding gravelly coastline. This is to illustrate the fact that most of the sediment that our rivers carry is silt, but it doesn't really play much in the coastline because it's just muddy water for the most part. This is the Rakaia River in flood, and you can sort of see the difference. This is the plume of flood sediment going out. This is the eroding gravelly coastline. This muddy water is what's always there when it's windy. It stirs up the mud along there. So this mud is part of the coastal erosion. But up here we have Lake Ellesmere Waihora and the Kaitereti barrier, which is where all the gravel's accumulated and building outwards. So the entire erosion of the Canterbury coast has been piling up at the edge of Banks Peninsula there through time. Boom, land strikes back. So this was an example of an uplift of several metres near instantaneously in the Kaikoura earthquake. The land scored a win. Obviously we only show pictures of the most uplift, and so this was where it went up 6 metres. But people are standing up on what was the high tide line, and it's now down where the little red line is there. So that's going to take thousands of years for the sea to get back that one. And in the longer term, you can see the traces of the rising land in the landscape. You'll make out this cliff line here. That's the last interglacial cliff line, about 125,000 years old. This terrace here was the shore platform. It's now uplifted 20 or 30 metres over 125,000 years. So the land is rising and the sea's not getting back to where it was each time. And then we have examples where things that just go nuts. This is Warrington, just north of Dunedin. They built the surf club. Nice handy dandy spot here. It's got 2 stories. You can stand on the terrace. You can see the sea and the surf. Everything's good. And then the sand started building up and building up and building up. And so it's currently now a 270 metre walk with your surfboard to get to the surf. And there's been a lot of discussion. Port Otago dredge Otago Harbour of sand, and they dump the sand off out of the way, just out to sea, and it's not far off here. And so the locals have a suspicion that might be a factor here. But do we understand enough about how it works? I'm not so sure that we do. So has the sea ever been a winner against the land of Zealandia? There's been a debate. regarding late Oligocene time. The interpretation here from Dominic Strojan and others is that there was a reasonable amount of land at that time of maximum submergence, but there is an Oligocene drowning hypothesis that the whole thing went under. And it's been an interesting debate. I personally think that there's a few critters, and so it's a case that the geological evidence, it's a bit incomplete, a bit hard to tell for sure, but I'm not sure how else you get a tuatara, an earthworm, and large flightless birds having been here until the contemporary, without there having been land. So for final thoughts, a geomorphological approach to categorise the Aotearoa coast, it gives a context to why the coast is like it is. And I think the energy and sediment budgets will give an aid to understanding and management of coasts. And it's really important to understand there's a lot of individualities throughout the overall system, whether it's in the rivers or on the coastline. And so it's always going to require a case-by-case approach to some extent to properly understand them. And I think with that approach, New Zealand will be better equipped to forecast coming changes in the shifting climate. Best guess, in large part, the future will hold a continuation of erosion or sediment building out or whatever's going on at present, although the rates may vary. But I think a proper assessment of that using relevant factors, but which may have been often overlooked, will at least reduce the potential for surprises. And so when the sea versus the land is the question before us, will there be a winner? I think it's perhaps better to regard the two as players, and if we work to properly understand the game, I predict that people will be the winners. Thank you.
Hi, thank you, David. Are there any questions?
Perhaps a bit off topic. You mentioned about a million years ago the sea level changes took place from. Thanks. You mentioned about a million years ago that the sea level variations changed from a 100,000 year cycle to a 41,000 year cycle, which is the present situation. Do you have any thoughts on what might have caused that change?
Well, yeah, so the supplementary lecture that I gave this afternoon that you were at on the Zealandia switch might be the answer to that. I would speculate that perhaps the Southern Ocean by about 1 million years ago had widened to a point where its configuration was in a sweet spot for the Zealandia continental mass in Aotearoa to influence the oceanic circulation enough to make us sometimes skip those 40,000 year cycles, and actually we get every second and a bit one. So I'd say that it's most likely tectonic in the same way that the general decline of global climate since the Eocene-Oligocene boundary, which can be linked to the opening of the Southern Ocean, is a tectonic thing. And I think that probably that change about 1 million years ago is likely somewhere in a tectonic explanation is my guess, and that might just be the Southern Ocean having got to a configuration where it's really working in that way.
On those sub-ocean valleys where the rivers were flowing in, you can see these channels sometimes running out like, you can see channels running out like 15, 20, 50K even. And you said that...
If not 500 in some cases.
And so I was surprised at that, because I'm thinking that even though you said that the sedimented water was heavier, would it be heavier than the salty ocean water?
Well, it's not my specialty, but I think we need an explanation as to why they're there. in fact that they start at the landward edge and then snake down, and the jolly things even meander. It's a fascinating feature, and you see it in the oceans around all the continents of the globe, these submarine channels, and there may well be people who can shed a bit more light on that. Lorna talked about this in last year's lecture, for instance. So yeah, I can't give you a firm answer on that.
Yes, Lorna is the key, because I think some of those features are not all eroded by rivers flowing, but they're actually shaped by catastrophic submarine avalanches, which are called turbidites. And there's a whole mechanism there that can be much more effective. And I think that also explains why a lot of them have different lengths. They're not from a stable system, but they're made by catastrophic events, which also have their individuality.
Lorna, would you like to jump in?
Oh, she's here.
Last year's Hochstetter.
Hey, I was just going to say that the submarine channels can actually be more than 1,000 kilometres long. So the Hikurangi Channel, which has its headwaters in the Kaikoura Canyon, goes for a really, really long way. And the New Zealand offshore margin is covered in numerous canyons, many of which link to substantial submarine channel systems. And in answer to your question, is the finer sediment plume of a high enough density to overcome the salinity of the salt water? It depends. But if we have a big flood and there's enough silt to the water ratio, the suspended sediment concentration indeed overcomes the salinity. And for some rivers, when they're in extreme flood, they continue directly offshore. But as Bernard said, in these canyons, we've got a lot more kind of submarine landslide processes. We also have internal tides that break at about 500 meters water depth and just trigger huge collapse down these systems that can be huge.
Hello. I can't believe it. We do so much dredging. Dredging is a terrible habit. Dredging rivers and dredging like the Auckland Harbour. When they dredge the Auckland Harbour, it's going to cause erosion around the coast and around the city. And then all the sand and whatever, they take it and dump it out around Barrell Island. Now in New Zealand, a lot of land has been reclaimed. And every time we had a flood with all these huge rains, we'd lose millions of tonnes of topsoil, all washed out the sea. And people talk about the silt, how disgusting the silt was. Get rid of the silt, sorry. And we need to bring the silt back into the land. You know, we're losing our land. We need to preserve the land. Everybody knows when you go to the beach and you start digging, like on the North Shore, if people start digging the sand along those valuable properties, the landowner will come out and say, "Get away, don't do that. You're undermining my land." They know that. Well, the dredgers are doing it by bucket loads in the Auckland Harbour. And most of our harbours in New Zealand are being dredged, and all the sand has been taken out and dumped out in the sea. Bring it back and reclaims the land.
Here.
Okay. Any supporters? Nobody supports.
He supported. He said here.
What?
He said here.
What's your comment?
He agreed with
Here.
Oh, thank you.
Unless you have ocean-going vessels.
And when they have these sandbars, they want to get rid of the sandbars and dig it all the way, make another channel, let all the sand flow out quicker.
If no one else has a question, I have another one. That when you were showing us the 018, 016, and the 018, I think at a scale 4, 3, 2, 1, 0, -1, -2, and I go, what is that scale? It's fascinating that we can understand how much ice there is on the land by how much 018 there is in the ocean. But what was that scale at the top?
It's a per mil scale of the ratio. So rather than percent, it's per mil 1,000th. And I'd have to, and I have to say I stole that diagram from someone else too. I'll have to check with them. I'll get back to you.
Hello. You touched on the NZ Sea Rise study, or the data set that came out recently, which has been pretty heavily used in industry since it was released. Just keen to get your thoughts on that from a more deeper time perspective in the work you've been doing, and I guess the work that you showed will be of quite interest given that recent study that's come out.
Yeah, I think it's valuable to look at everything from a range of perspectives, and I think that we now have the satellite technology to either through satellite radar and through the GPS, continuous GPS surveying, we can get some amazing perspectives on contemporary changes, which I think is really useful. One thing that's been a great step forward is the current iteration of the NZ Sea Rise. They've put uncertainty onto these numbers, which they didn't have before. So the original data set had two significant figure values but no uncertainties, and so now they've put uncertainties on, which is really helpful to understanding. And so for instance, if you've got a 0.5 millimetre per year change indicated, it's got about a 2 millimetre per year uncertainty on it. So that's, I think, a very useful piece of informing, because without that uncertainty, it was quite hard to reconcile some of those raw, precise numbers with geological process, and they were, you know, quite different over a short space of distance, which was very difficult to reconcile as a geological process. So I think the uncertainties will help to inform things, but the main thing is that we're now able to measure things that we could never ever measure before, which is these very precise changes in ground position and ground elevation. And for me, the real wake-up call for this was once they'd had a couple of decades of doing a continuous GPS installation surveying based in Dunedin. They looked at the data trend over those 20 years, and they spotted 2 Fiordland earthquakes in the data set. So 2003 and 2009, they had magnitude 7+ earthquakes in Fiordland, which is epicentres close to 300 kilometres away, and yet the ground level changed in Dunedin by, you know, millimetre or two, but it was distinct and very believable. And even that was just the vertical. There was also a horizontal shift, which was larger. And for me, I then could look at a map of Aotearoa New Zealand and see that, you know, in the northern North Island and southeastern South Island, the land ends about 200 kilometres from the plate boundary. And so that's the plate boundary deformation zone, and I see those minuscule effects of those Fiordland earthquakes as far away as the east coast at Dunedin, and I think, well, that's why the land's there, because that's the far field effect of the uplift of these big plate boundary earthquakes. And so for me, it really highlights the value of our ability to measure these things that we could never otherwise measure. And by the same token, I think to integrate those contemporary measurements where, there might be some transient geological processes going on that's causing the land to rise or fall in ways that we wouldn't predict long-term geologically, that might be some sort of transient effect. So I think that, together with the longer-term perspective from the geology over, 100,000 years from where the last interglacial 125,000 year shoreline is it, is it 100 metres up in the air like it is in some parts of the southeastern North Island, or is it is that same shoreline now buried 30 metres under eastern Christchurch where it's been subsiding? I think that those perspectives are important, together with the contemporary measurements. They're all helping us to improve our understanding.
You've showed us very nice maps
of the former extent of the glaciation in the South Island. Now I'm going to ask a silly question, because actually there's a lot of uplift happening there. Could there be a signal of the unloading of the melting of the ice in the sediments?
So that's been a point of debate and thought over many years. In fact, there was a paper published on it the year I was born from a Canadian glaciologist. I think that the thing is that in the Southern Alps, the ice, for most cases, only formed a few tens of metres, and then it would flow off down into the valleys. It would be thicker in the valleys, maybe hundreds of kilometres thickness of ice. And when that melted away, it left a puddle of water. So that the ice didn't, the mass of the ice didn't completely vanish. So it left a third of the amount of ice was left as the water in those lakes. And then they've been filling in with sediment as well, coming in from the mountains. So I think on balance, the feeling is that the ice mass wasn't enough to have a big effect. Because it's it's just the nature of it. It's a very different situation to areas of continental ice sheets in the northern hemisphere, where British Isles, for instance, were covered with ice. Many hundreds kilometre or so thick. Scandinavia had maybe 3 kilometres of ice on it, but it hasn't really been replaced by anything. The ice is gone. And so that's where you've seen big rebound. So I think it's another case where they need to look at it case by case.
Okay, so thank you everyone for coming out on a bit of a dirty Auckland night, and for the Auckland Museum so much for hosting us. But let's just give our speaker, David Barrell, one round. So we're pondering whether to convene in Tui downstairs for a drink if anyone would like to mix and mingle and discuss anything further, but thank you.